so not too bad there, okay? How many have ever heard of the Romi robot before? So that's good, about at 50%. So today we're going to talk about starting to learn to program with the Romi. And one of the reasons why this was envisioned is we worked with a group, a couple of engineers out of Bloomberg, who were coaches, and they basically decided, how do we get kids earlier into programming? Oftentimes on an FRC team, you don't have access to a fully built robot to learn to program, right? They're all building the mechanical. It's what used to be bag day back in the days when I was an FRC coach. And you didn't have access to actually learn programming. So this was designed by the engineers along with the WPI library for you to do just that, okay? So that's kind of in a nutshell the way this started. A little bit about me, sorry, gotta switch hands here. So my name is Lori Birch, and I am a curriculum developer. I'm on the education team for FIRST. So I've developed the FIRST Tech Challenge class pack curriculum, as well as now as the intro to programming modules that you have available through your dashboard for the Romi. A little background from myself, where did I come from? Why am I here? I was a coach for about 15 years. I started with FRC. I did FRC in the middle of the mountains in Colorado with an hour from the nearest Walmart and 100 kids in the high school. So it was a bit of a challenge. So I decided to go to FTC, and then I did FTC for 6 years. And then the other thing I do is I work a lot with workforce development for FIRST. So we're working more towards how do we help with CTE pathways? How do we help students with their own learning pathways so that you guys can get industry certifications? How do we help you have that right path to say, okay, I want to become a programmer and take this route? And how do I get that industry certification that then lands me a job with one of our sponsors? So this is actually this project was one of the first things that we actually decided to start this pathway with. And that's many of you. How many in here have actually taken like an AP Java course? A few, okay, but not many. One of the big challenges that I even found as a coach was that I had students take AP Java. They still couldn't transfer that knowledge to a robot because the programming infrastructure is quite different. And that's actually one of the other things we're going to kind of cover a little bit today. So, what is the course? So all of you have access to this course. Your lead coach or mentor actually have access to the course they can invite you to. So it's available on the FIRST dashboard. The learning management system is a little bit clunky. There's more seats over here if you guys want to come on across. But once you get in there, the course is pretty easy. It's self-paced. It's not meant to be a grade. You guys are all individual learners. We know that FIRST students want to learn on their own. They want to get better on their team. So it's not necessarily meant to be a teacher's assignment or a grade, but it is meant to be a learning pathway for you with some interactivity, with some videos, and you know, kind of a good scaffolded learning. There's 2 different modules. So the first module goes over setup of the Romi, programming robots in general. So very, very basic. Goes over the very, very basic fundamentals of Java, of using objects and methods. So if you've never taken Java programming before, you can still do this course. You don't have to know that much. This leads you through that very basics. I'm going to dive a little bit more into the advanced portion of that today, and really dive into command-based versus time-based programming. But I would highly suggest if you find yourself like, I don't know where I'm going in this, or this seems above my head, go back and do these. This starts you out with those great fundamentals for a Java course. These are the same things you would learn in an AP Java course. So it's things like objects, methods, classes, inheritance, and conditionals, and then variables and equations. The benefit to this, though, is we do put this all into the FRC Romi and to programming a robot. So it's not how you would learn in an AP Java class because they do it more on other things that may not apply to your real life. This is all real-world based with your robot. Module 2 then goes into command-based programming, arrays and loops, driving and inputs, so you actually don't get to drive the robot until driving and inputs, which is sometimes a challenge. How many of you have autonomous programming on your FRC robot? You guys are all world teams, so I'm sure you do. How many teams at your local qualifiers do for your beginning? If you were a rookie team that didn't have anybody else with any experience, would you have an autonomous robot? Especially if you only had a 6-week build season. Now a lot of people's build seasons have expanded a little bit, But this has helped meant to ease that learning curve. So you at least can get a driving robot with some autonomous programming and understand how to program those sensors in that command-based framework. We also go into command groups and interpreting exceptions. That goes with how do you find errors, how do you track errors, and where are errors occurring in your program. That's kind of the overview. If you would like to access the course, this is kind of a demo of the course. This is the second module alone. We'll see if my luck, the QR code won't work because we know technology and that's what it does sometimes. But this is a direct link to the Rise 360. I'll probably password protect it after this, just so you know, so you can't go back and get it later. But for right now, if you want to follow along, the internet in this building we know is not great. So I have everything that you'll need today. If you can't access this right now, you still can access it through your dashboard, and I have the directions for that once we finish today to get to your dashboard. But this is if you do happen to get the internet to work and you want to follow along and see. There is more interactivity in the online portion, so there's like quiz questions and some things like that, that if you were doing it as a student, knowledge checks for yourself. We're not going to do those necessarily today, but they are in the online. So learning outcomes of this particular lesson is to differentiate between time-based and command-based robot projects, write command classes in the FIRST Robotics Competition programming, explore robot hardware as subsystems, analyze the gyroscope hardware, and use it to control your robot and create and schedule commands for your robots. So we're going to use, with the Romi robot, if you're not familiar with the Romi robot, and I hope you can kind of see this, I didn't realize the size of my room. I should have looked at it ahead of time. And I was going to try to do a video camera, but that was going to be more trouble than it's worth. So the Romi robot is basically an Arduino board with a Raspberry Pi on top. And then I have more I can pass around for you in just a minute, too. Just make sure I get those back. Those are on loan from a team to me. And this one is slightly different than that one. But they all are basically available through Palalu. And Palalu is going to send you a basic kit. The basic kit from Palalu comes like this, though, and does not have a Raspberry Pi. So the big challenge today is finding the Raspberry Pis, because they have the same chip interface that everything else does. That's a little bit of a challenge. So, but if you have a Raspberry Pi, it's a Raspberry Pi 2 Plus that you order with it. And then there's basically an image that you can download to the SD card. You image it. Yeah. You have to look at, so there, how many of you have seen the link on the WPI library for Raspberry Pi 4? Or for the Romi, I'm sorry. So we would have to look that up. I think it might be, but I know the 3 Plus is the version that we said does work. You could probably try it with the 4. What I do know is the same library that this uses is the same one you would use for vision processing on your FRC robot. So it's that same image file from, I guess, the infrastructure or the repository of code that's on the WPI library. So if it works with if your image processor works on your robot with a Raspberry Pi 4, this probably would too. Does that make sense? So it uses the WebSocket. Basically what you're doing is you're running the program on your computer with VS Code, and then you're just controlling, this becomes your wireless device with an Arduino-based board. So what type of sensors and hardware do you think are on this robot? Go ahead and raise your hand if you want to. It does not have a color sensor on the bottom. Yeah. Gyroscope, great. Anybody else? Back there in the back? Encoders. So you have encoders, you have a gyroscope. It also has 3 LED lights on it. And the LED lights are little push buttons that are on the Arduino board that it's right up here. So those are the other kind of inputs and outputs. And all of this kind of has that same technical documentation that you have. It's in the WPI library. If you take the course, that is also embedded into the WPI library. So it takes you, or the WPI library is embedded into the course. So it's embedded via an iframe. It takes you right there. You can explore the WPI library in conjunction with the content. So let's first take a look at a little bit of, Romi hardware, so it has a drivetrain, it has encoders, onboard LED, gyroscope. I think the only other one we had that somebody maybe didn't mention was the accelerometer. All of those can be used as sensors. Are those valuable sensors even on your FRC robot? Those are all in that same WPI library code that you may use on your FRC robot, but you can actually learn to program those with the Romi. So this is one of the videos we have that kind of goes over what is command-based programming, if you're not familiar with it. Oh, I say that, and of course, I love technology. There it goes. Now, do I not have sound? That's the one thing I didn't check. Where's it coming out at? The projector. Oh. Well then. And that's at 100% too. I thought it was hooked into the sound system, but it's not. Pause. I'll just take this mic and put it over there by the laptop. I just have to get to the back to this beginning of the video. Okay. Technical difficulties, you gotta love it. I plugged everything in thinking the HDMI would work and audio, and it didn't, of course. Play, go back. Come on. Why aren't you? I was doing good. I thought I had it, and now it's not. One thing about championships, you always get your exercise. Anybody tired of walking yet? I decided to add just a few more steps to my day because I needed that. Okay, now if I hit play.
The programming robots lesson of this course, you were briefly introduced to command-based programming, but thus far you've used a time-based robot template for all your projects, in large part because it's quick and easy to get started. There are a lot of advantages to using command-based programming for more complex tasks. Let's start by discussing what command-based means and why it can be useful. When you think of a robot, you probably think about things it's capable of doing. For example, it might be capable of driving forward, turning, and stopping, etc. If it were a warehouse robot that had a lift, it would be able to raise the lift, lower the lift, and stop the lift. If you were telling someone who was operating the robot what to do in a step-by-step process, and they were trying to move a box, you would give them instructions such as drive up to the box, lift the box, drive to the location where you want to move the box to, and so forth. Command-based programming lets you issue tasks to your robot in the same way using code, such as lift box. This lets you code your robot in a way that mirrors logically how you think about it. In addition to commands, command-based programming uses the concept of subsystems, which represent the physical systems on a robot. For example, if the robot had warning lights, it might have a lights subsystem. You can use your imagination to think of other subsystems that a warehouse robot might have. In command-based programming, it is this subsystem that can be issued commands. In this example, the robot's drive subsystem would be issued the command to drive up to the box, and later to drive to the next location. And the lift subsystem would be issued commands to pick up and lower the box. In this course, you won't be creating any subsystems. The Romi command-based robot project template provided in the WPI library contains a drivetrain subsystem class that has the Romi already configured. When coding your competition robot, you will make several subsystems that represent different mechanisms on your robot. A command can use a single subsystem or multiple subsystems at once. Continuing with our example, in a simple command to drive forward, it might only use the drive subsystem, but you could create a command that drives forward and raises the lift at once. A fundamental concept in command-based programming is that each subsystem can only be running a single command at once, and if a new command is issued to a subsystem, it will terminate the previous command and start running the new command. This makes intuitive sense. If you issue a drive command and then issue a stop command, you want the robot to stop. If one line of your code is telling the robot to stop, but a different line is telling it to drive, it will stutter, which is not what you want. You do not want the robot to drive and stop at the same time, which sounds silly, but it's actually a fairly common problem that can occur within a time-based robot template. With command-based programming, as soon as the stop command is issued, the previous command, drive, will end immediately. The robot will only execute the stop command. If a command acts upon multiple subsystems, then all commands being run by any of those subsystems will be ended. Another big advantage to command-based programming is that commands can end themselves. Each command includes some code that repeatedly checks to see whether it's done. If it's not done, then it keeps executing as normal. If it is done, then it will end itself, and you can specify any behavior you want to occur when it ends. Contrast this to a time robot. With time-based robot, your robot will contain many conditional statements within the periodic method that constantly loop. In a robot with many mechanisms, time-based robot code will be centralized in one place and may be difficult to troubleshoot. This creates situations where you may not know why your robot is acting in a certain state. For example, maybe you know that your robot is driving forward, but you don't know if it's driving forward because you want it to drive forward for 5 seconds or if the operator is pushing down a joystick. With command-based programming, the logic is separated into commands, making it more convenient to debug and prevent errors.
So that's one of the first videos, or one of the main videos on command-based programming. So using the Post-it notes and the piece that I gave you, choose a subsystem. So it could be the drivetrain, onboard LEDs, gyroscope, or accelerometer. If you did not get a piece of paper and sticky notes, you can do this on your phone or any other piece of paper you have handy. Just write down, work with 2, 3, 4 people next to you if you're in a team. Come up with 3 or 4 commands you would like your robot to do. This is all pseudocode. We're operating in pseudocode today because obviously I can't provide every single one of you with a Romi and sit down with a computer and program it. So we have to do the best we can. So you're choosing a subsystem, and then you're writing at least 2 pseudocode commands for your subsystem. Anybody ever told you how to break down the word pseudocode? What's pseudocode mean? What's pseudo mean? Fake or false, right? Everybody heard of it like a pseudopod, which is in biology? I used to be a biology teacher too, so I always reference it. Pseudopod is like the long feet that an amoeba has, if you've ever seen an amoeba, which is like that single-celled organism that has the legs that extend out. So that means false feet. So this is false code, so it's code written in the form that you can understand and not necessarily the computer can understand. does. You're right. You're on the right track. You're on the right track. Drive forward would be one command, right? Using the drive train. What's another command you might have on that hardware? List all of them, right? Okay, so did you list those down? Or have you listed them down in your group? All right, so does everybody have their list or they need a little more time? Raise your hand if you need any more time. Not, we're good. You need just a little more time? Okay, I'll give you a couple more minutes. Okay, so I've walked around, talked to a few different people of what you've got. You know, I've seen a lot of people that have their drive system, or they're using the drivetrain as their subsystem, and their example of their pseudocode or their commands would be drive forward, stop, turn left, turn right, maybe drive backwards. You might have, did anybody have Gyroscope? I thought I heard a couple of people talking about that. Did anybody actually use Gyroscope? What might you have as like actions for a gyroscope? Let's go back over here. Turn on the gyroscope, okay. What else? Reset. Back in the back. Get information from the gyroscope. What's it gonna, what type of information is the gyroscope gonna gather? Orientation, so what degree is it, left or right? But does it also, can it also do roll and pitch? This one actually, I believe, does. Don't hold me to every little detail, but the final program is really just left and right, but it does also do roll and pitch as well. Anybody else have anything else? Did you have something else you wanted to add? Okay. So next we've got to figure out, okay, so now we have what we want our robot to do, right? What's the next step though? What makes command-based programming? We could write in a big long thing that says drive forward, turn left, I'm an animated teacher, you just got to live with me. But right, we could have this long sequence of commands that goes one by one by one by one, right? Each chair could be a command that we're doing for our autonomous routine, right? Can that easily get messed up over time? How many of you guys did FLL? And how hard was it to get that robot? If you did one long sequence of code all the way through, how hard was it to get that robot to actually do what you wanted it to? If you didn't use different things you're putting in at a time that you had controlled, right? What'd you do? You got it to go back to home base so you could restart it. Same basic principle here, it's just in text code expanded. So in command-based programming, they've created these different little options that you do. I gotta get back over here so we have sound, so I don't mess up this time.
In the command-based paradigm, there is one class that is responsible for managing the state of commands, called the command scheduler. Let's look through the code in an example project. First, open the Romi reference project you created in the Robot Programming Structure lesson. You will use the code within the Romi reference example to explore the structure of command-based programming. Open robot.java and scroll down to the robot periodic method. You can see that the command scheduler runs constantly while your robot is turned on with robot periodic. The command scheduler looks at all commands in your code, figures out which of them should be started, executed, and ended, and performs those actions. In the process of doing this, the command scheduler is looking for specific things in a command, for example, the execute method. It will call the execute method when the command should run, and it stops calling it when the command should end. We've also discussed how only one command can run on any given subsystem at once. The command scheduler is what manages this, overriding old commands when new commands are issued. You don't need to understand the inner workings of the command scheduler, but you do need to understand how the command scheduler processes commands. Let's dive into the different portions of a command. Open the drive distance class. Every command contains 4 methods: initialize, execute, end, and is finished, which are the 4 main features of a command. As you might infer from the name of the drive distance class, this command makes the robot drive a specified distance in inches. Let's go through this command line by line and gain a complete understanding. First, the class is declared, and the extends command base specifies that this class is a command. Extends means that the drive distance class is a subclass of the command base class, which is the class name that indicates that it is a command. After this, there are 3 class fields declared: the drivetrain system to operate with, the speed, and the distance. This is the constructor for drive distance. Remember, constructors have no return types, and their method names match their class names. Only constructor methods have these features. This constructor initializes the class variables declared, and calls the addRequirements method to specify that this command requires the drivetrain. Specifying requirements is how the command scheduler knows how to manage which command runs on which subsystems. These lines define the initialize method for drive distance. In this case, the code tells the robot to stop by giving it 0 power and 0 turn. We reset encoders to make sure that they're measuring from 0 when the command starts. If the robot has already been driven around or rolled by hand when the command starts and the coders weren't reset, then the distance measures would be wrong. These lines define what the command should do while executing. This command is called drive distance and only drives in a straight line, so this method is pretty simple. Drive the robot with the speed specified when the command was initialized, and supply 0 power to turning to go straight in a line. As this is the execute method, it will be called continuously while the command is running. These lines define the isFinished method of the drive distance class. All of the other isFinished methods we looked at so far simply return false. For driving a set distance, we want to stop after the distance has been driven, so this isFinished method actually needs to check that. In this case, the code calls a method called getAverageDistanceInch, which returns a number of inches that the robot has traveled using the encoders, and compares it to the distance the robot is supposed to travel. Let's take a look at how the getAverageDistanceInch method works. Press F12 to be taken to the method, or right-click on the method name and select Go to Definition. Within the drivetrain.java class, you can see that this method takes an average of the left and right encoders by adding both encoder values together and dividing by 2. If you'd like, you can continue reading code in this class to understand how the encoder values are read and converted to inches. Return to the isFinished method of the driveDistance.java class. If the distance traveled is greater than or equal to mDistance, isFinished will return true. And when that happens, the command's end method will run, and then the command will be over. In this command, we want to measure the distance traveled in any direction, forwards or backwards, to be compared against the required distance to travel. To accomplish this, we will take the absolute value of the distance so that both negative and positive values returned by driving either forward and backwards are compared to a positive driving distance. So here we use math.abs, the absolute value function in Java, because the distance returned by getAverage distance inch will be negative if the robot is driving in reverse. These lines define the end method, which, as the comment states, is called when the command either finishes or gets interrupted. Commands end when their isFinished method returns true, and the most common way to be interrupted is if another command that requires the subsystem is scheduled. For example, you could add code to your robot such that if you press a button on your controller, it immediately defaults back to operator control, which would interrupt drive distance because the operator control requires the drivetrain. We've now looked through the entire line of code in this class, and hopefully you now have a decent understanding of an entire file of Java code. Obviously, there are still a few things we haven't gone in depth into just yet, but you should now understand the various methods and why they exist.
So what I would like you to do now is, using your same piece of paper, Post-it note, phone, whichever method you used, choose at least one of your commands and write the conditions or what are the values or hardware parameters that you would have during initialize, during execute, during end, and during isFinished. What would you want the robot hardware to do in those states? So pick drive forward, turn, at least one, if not two. The other idea, you could expand this even further and say, okay, how could I use these commands to trigger the next command to happen? I did have somebody ask a question on the Romi. So does this work the same as your driver station with FRC? That answer is yes. We haven't gotten to the part where we're running the simulator and everything yet, and hopefully we'll get to it. But this does work. You use the simulator on your dashboard. So the simulator that runs within the, it's not within the WPI library. It's the other extension you add to it that I can't think of off the top of my head. So it's one of those tools you download within the FRC toolbox. And I can show you that part of the video here. That's the next video if we dive into it. So I had a gentleman over here that got my attention, and he brought up kind of a good point. What happens if you happen to be the mechanical person on your team? Is it still valuable to know this? Yeah, why? Because you need to know what to tell the programmers to do. And how many fights are, I don't want to say fights. Let's say how many disagreements and or heavily intense discussions are there on FRC teams on whether something isn't going right versus mechanical versus programming, right? So the more knowledge we all have, even if it's your mechanical person that's doing this in the off season, not because they want to become a programmer, but because they want to understand more about how when they design something, they can design with that data and that end in mind in that process. So they're designing and they're implementing the sensors and some of the electrical components that the programmers are then going to need. And then they know what to tell the programmers. And it can really help you decrease that tension or that, well, I guess you would more call it maybe disagreements in the knowledge of discussion, of understanding the problem, right? That might be the more gracious professionalism way to say it. Okay, so anybody have any questions on this? Anybody have an example they want to share? No? Is this the scary part of it, the initialize? And some of this is you have to think about how often on teams do we forget to decide what data value does my hardware need to start at? We get used to just starting with a controller. We don't think about, okay, it needs to start in this position and end in this position. Yeah.
I got check your position, and if the position-related variables are anything other than 0, change them until they are 0.
There we go. So in initialize, if it's something other than 0, so if that arm is out of place and it needs to move to the position of 0, you want it to do that, right? You just don't want somebody's hand to be in the way when you do that. So that's another one of those safety protocols. Huh? That makes it, no, we won't say it makes it even better. I would have to disagree on that. Okay. So how can you use this? What's the next step? So this is available to each and every one of you. You might have to hit up your coaches just a little bit, not just your coaches, your lead coach, mentor 1 or 2. So the only people that have access to it have access to invite you. So as soon as they go on, these are the directions that'll take you to the directions for the dashboard. This is also in the FRC blog from last end of October, I believe. November. It's Intro to Programming with Romi. So if you get lost, this link doesn't work, you can go search that blog and it goes through and discusses all of this with you. And it'll show you how to get there. It'll give the directions. You can send your coach to that direction and say, hey, we think this would be really valuable. This will take you to the ThinkScape directions directly that you can share with your coach and say, can you please add me to this course? Once they get into ThinkScape, they can put in your email. They add you to the ThinkScape course. that's associated with your FRC team. They invite you as a student to that team. If you're the lead programmer on your team, they can invite you as a teacher in that course, so then you can help guide other fellow students in the course themselves. And this was just a sample of that command-based programming lesson that's in the start of Module 2. So this, we've kind of just barely touched upon it. The next part of this lesson actually dives in and has you write commands for the gyroscope, and you go further deeper into that. We don't have time to do that today because that would take a little bit longer, but it is something definitely you all have access to. Questions for me? Anybody have any questions? Yeah. How expensive? So the course is absolutely free. The Romi robots run, I think, Palalu had a grant for 112 that you could order. This is all linked on the WPI library. If you look, there is I could probably pull it up if I need to on my computer. There is a link. If you scroll down on the WPI library, it's basically Intro to Romi, or you'll see that, and it shows you the directions on how to go to the Palalu website and order. When you get that Palalu kit, though, it's going to look like this. And it's not going to have the Raspberry Pi attached. That's where you have to find the Raspberry Pi and the SD card outsourced from another source. And then the WPI lib also has all of the directions to image it, to connect it, to enable the web socket and make sure it's up and running. And that's one of the first lessons you learn in this particular activity. Any other questions for me?
Can you talk about the simulation environment and how that works with the Romi?
Let me see here. I will see if I can pull it up real quick on my computer. So the simulation environment, basically what happens is when you're in the WPI, or when you're in the VS Code, right? So you start up VS Code, you hit F5 as long as the simulator is installed, it'll automatically open up. And then basically if you have a joystick plugged into your computer, you automatically drag it over and you can run that in autonomous and execute. Let me see, hang on just a second. I'll see if I can pull it up and show you a program here real quick. Are there any other questions I can ask or answer while I'm doing that, and I can pass the microphone around? So if you're in VS Code and you hit F5, that simulator will pop open. It starts your full entire project. And then if you are connected via the Wi-Fi, and so I don't have the Romi turned on right now, so it's probably going to give me an error and not work. But I can show you where you hit initialize, and where's the blue Romi? I can turn him on and see if we can get him connected. Where's my... So you'll see the simulator pops open, and then you have, and the tutorials walk you through this step by step, but you'll see that there is, you can run it just with your keyboard if you have to. If you have a joystick, then you can run it with a joystick. And you see those variables down here. But basically, once you create your code, if you're connected via the Wi-Fi network of the Romi, so once he powers up, maybe, see how many hotspots we have open today. I feel like I'm being an FTA right now. And of course, he's not popping up because it takes time. But basically what happens is once you connect to that Romi, you then can just run the simulator. And once you hit autonomous, you select the button right up here with autonomous, teleoperated, and test. And it'll run automatically with whatever code you have back here. And so you can see back here, it's like connection attempt, I'm not connected, because even though I turned him on, it takes him a little while to get up and running. And he'll show up over here as a, if he's configured correctly, it'll show up as a WPI lib, something or another. You know how they have all the serial numbers sometimes. Come on, Romi. But that's basically how you use the simulator from there. So if I were to run, you know, I can select an autonomous program, a teleoperated program, or a test program. And like I said, it does take you through that completely. Did I connect already? Oh, it did. So if I were to run, I think it's, I don't know what program I have on here right now. Disable. So if I run the autonomous, his batteries are almost dead, but you can see he's running right now. And he's running whatever I have in that autonomous command right now. He's kind of running at the side. It's a little bit hard to see, but. And so I think one of the programs, I think it was in autonomous, but one of them we have is actually in teleoperated. Disable. One of them we basically have also where the LED lights will change based upon, so like if I have the gyroscope, I can get the LED lights to change based upon the rotation of it. I have to reset it and set it on the ground and reactivate and all that stuff. But without the right camera to display up there, it's a little difficult. Any other questions? Well, I want to thank you all for coming. I think we are just about out of time. If anybody needs my contact info, again, my email is up there. And I hope you have a wonderful day, and this was a valuable resource for you.